7, Section D, we're going to finish up the chapter on chemical reactions today. So chemical reactions occur at different rates, okay? The reaction rate is literally the rate of the reaction. It's just the speed that the reaction takes place, okay? This collision model, or this collision theory, explains the different factors that have an effect on the reaction rates, okay? So there's three things that need to be true in order for reactions to occur. The particles must collide. They must actually hit to come into contact with each other. They must hit at the correct angle in order for a reaction to happen, and there must be enough energy for a reaction to occur, okay? So because of those three things, there's lots of different factors that affect those things, okay? So the next slide are the factors that affect the reaction rate. The first thing is the surface area. If you have ever dyed Easter eggs before, got that little tablet that you drop into the cup, okay? The tablet needs to dissolve, all right? And so the whatever shape the tablet is only in contact on the surface of it, okay, on the outside. But if you take that tablet and you crush it up into a powder, now all of a sudden the reaction can happen on much more areas, and so it's going to dissolve much quicker, okay? That's actually a picture of a grain elevator. That's something we don't have out here in Southern California. That's in like the Midwest and farming regions. What happens sometimes is you've got this dust or this grain that settles into an elevator, and it doesn't have very much surface area, just the top of the stack. If it gets stirred up and there's all kinds of dust in there, all of a sudden you have all this surface area that can combust. It can have a reaction, and if there's a spark, if there's static or whatever, because of the additional surface area, a reaction can happen and they blow up. I will show that to you in class. Not an explosion, but kind of. Anyway, stirring can affect reactions. They can speed up a reaction because as you're moving the products, or I'm sorry, the reactants, as you're moving them, you're increasing the collision rate. Okay, so you're helping that happen. Temperature. As temperature increases, particles are moving faster. Faster it's moving, more collisions will occur. So that will increase the rate of reaction. So if you ever get a glow stick and you want it to last longer, stick it in the refrigerator. That's going to slow down the reaction and cause it to last longer. Some people store their batteries in the refrigerator for the same reason. A battery is a slow chemical reaction, releasing energy. If you put it in the refrigerator, that decreases the temperature, it decreases the motion of the particles, and so the reaction rate goes down. Concentration. If you have a higher concentration of a substance, you're going to have more particles. If you have more particles, then that collision theory will happen more, and you'll have more of a reaction. The presence of a catalyst might increase the reaction rate. A catalyst is just something that lowers the activation energy. Okay, remember that activation energy is the energy needed for a reaction to occur. Sometimes there's enzymes that can decrease the activation energy, and so the reactions will occur more quickly. But there's also the opposite. There's these things known as inhibitors, which then slow down a chemical reaction. Okay, they kind of prevent it from happening. All right, so we get this thing known as equilibrium in reactions. And equilibrium it's equal. It means something is balanced. Okay, and when it deals with chemistry, it means that the system itself is balanced. Some reactions are known as reversible reactions. So the reactants turn into products, but then sometimes the products turn back into reactants. And so instead of just having, whoops, let me get my pen. Instead of having, A plus B and then a single arrow like that, this reversible reaction would show both arrows, okay? It means that the reaction is happening, but it might be unhappening as well, okay? It's going to find a balance, going to find the equilibrium there, okay? So we can see equilibrium happening with forces, with physical changes, and with chemical changes. With forces, if the forces are balanced, then there's no motion happening. So if you're playing tug of war and both sides are being pulled exactly equally, nothing's going to happen. Okay. If two people are pushing on something and it's an equal force, it's not going to move. It's only when it's an unbalanced force that movement happens. So equilibrium would be that equal energy. Okay. It cancels out. Physical changes of state in a closed system sometimes happen. So if you have like a cup of water that's sealed, some of that water is going to evaporate. It's going to evaporate into that sealed closed system and turn into water vapor, but some of that water vapor is going to recondense and turn back into liquid water. That's going to happen for a while, and then it's going to find a balance, and it's just going to hang out. It's gonna happen to the same extent, and so you're not losing all of the water, but it's not all recondensing back. It finds a balance. Okay, and that happens in those chemical reactions, like I said, where the reactants can become products, and the products can become reactants as well. So we can change that equilibrium, and you can think of this as a teeter-totter, okay? And this is known as Le Chatelier's principle. I'll just read it to you. It says, if a dynamic equilibrium is disturbed by changing the conditions, the position of equilibrium moves to counter the change. So think of this teeter-totter here, okay? This is called the fulcrum. Right now, they're totally balanced. If I add another person right here, the teeter-totter is going to tip, right? And so I would have to move the fulcrum to a different location in order to rebalance the teeter-totter. And that's true with these chemical reactions, okay? If I change the concentration, I'm going to shift the equilibrium to the opposite side, okay? So if I add more of one substance, the equilibrium, it's going to cause the reaction to drift more to that other side. Temperature. One side releases energy, one side absorbs energy. Depending on what reaction's happening, the reactants might release, they might absorb, but then the products will do the opposite. So the reaction will move to one side or the other in order to balance that. And then finally, pressure. If I increase pressure of a substance, those particles are getting closer together, and so they're more likely to collide, okay? So if I increase the pressure, the reaction will go towards the products, okay? Because more of a reaction is going to happen, and so the equilibrium needs to shift. If I release the pressure, it's less likely to happen, and so the equilibrium is going to come back towards the reactants to try to speed that up, okay? Kind of complicated, I know. Do your best. All right. That's it for chapter 7. See you guys.